Okay, well, what we'll do is stop here, and we have time to discuss our paper of the day, a week. And so let me get it. It's up here. Can I hand it out to somebody? I thought I had it with me, but... Oh yeah, here it is. All right, can you get the light up, or the sound up for the people? Well, does anybody have any particular questions about this that they don't understand?
I have a question. On page 2359, it said it's the second paragraph in the results and discussion. And it said, Figure 1 shows the current over voltage relations during anodic polarization and high current densities, and the overpotential were found to be significantly larger than that for lead oxide. That's a disadvantage, right?
Yeah, that would be a disadvantage.
Okay. And I got confused in the third paragraph with the band gap and valence band level.
Yeah.
I got a little confused in there.
Well, that's a little bit different things going on here. Let's take some of these questions from the beginning. I think to first understand that problem, let's consider first about diamond. Diamond is not known to be a conducting material. If we have a diamond and a diamond ring, it doesn't conduct electricity. But does anybody know why this particular material is conducting electricity? What's the reason? Why is it conducting?
Because of the doping with boron?
Yeah, the boron is added in this case, just like we can dope silicon with some impurities, they can dope diamond with boron. Acts like I think a p-type semiconductor in that case. And adding a large amount of boron dopants causes the material to become basically a semiconductor. It doesn't really act like a metallic electrode, but it maintains most of its diamond-like properties, but now is conductive of electricity.
What they are doing is reducing that band gap, right?
Yeah. The idea, first of all, there is, you see, they say on that third paragraph, that as we're talking about, the band gap of diamond is 5.5 volts. With the valence band level about 0.7 volts. So in other words, there's 5.5 volts of band gap. In other words, it would take 5.5 volts of energy to get from an electron from the valence band to the conduction band. That's why diamond doesn't conduct. Putting boron dopant ions or boron dopants in there causes the band gap to close, or in other words, there's an intermediate set of holes that allow that to happen. Basically what they're saying is that by adding boron, they're adding the hole type. For semiconductor materials, you're adding holes to the material. In other words, they're positive current carriers to the system. And they correlate the increase in conductivity and the decrease in the overpotential required with the increase in the dopant density. A little bit, some of that stuff is a little bit beyond the normal, what we'd normally consider in electrochemistry at this point. We'll talk about semiconductor electrochemistry towards the end of the class, where that would make a little bit more sense. Basically, it says when the electrode is anodically polarized beyond the potential of oxygen, EO2, the material is acting like a metal because we've gone beyond the band gap for the system, and at any point beyond that, we're acting like a metal. Electrons can directly be taken out of the conduction band in that case. So to reduce oxygen, or to produce oxygen, the electrons can go right into the conduction band. I think there's a couple interesting things in here. First of all, you can see they're talking about current densities, 10 amps per square centimeter. And it's a fairly large amount of current, which is important really because, well, they're doing electrolysis of water. Now, do you suppose they're really interested in using diamond electrodes to produce oxygen or hydrogen in the system, or not? I mean,
What was the question?
they're using diamond electrodes to produce hydrogen and oxygen in the system. Do you think these are would be a commercially viable way to do this?
Well, I don't think so, because compared to what is used commercially, the overpotential is so high.
Yeah. They usually use a lead oxide electrode to make oxygen because the overpotential is very low. The lower the overpotential, the less voltage you have to apply to the cell. It means it's a more efficient process. There was a possible advantage, though, and they mentioned that at the end. I think that was at the end. Yeah. It says right at the end, lead oxide, the last paragraph, it says lead oxide is one of the most prominent anode materials, but it has to be protected from the chemical reduction by applying an external trickle current. What do they mean? Do you think everybody knows what they mean by that? What do they mean by chemical? Why would it have to be protected from chemical reduction? What are they saying, basically?
Could be deposited as lead hydroxide.
Right. Well, if you just have it and say sulfuric acid, it's not stable. You're just going to reduce. It's going to basically, you have batteries or lead oxide, so it makes a galvanic cell with just by itself. So it has to supply some external current to buck out the natural reduction by the materials. But platinum, so in other words, when the cell is not working, they always have to supply some electricity to the system to keep it going. This is not a situation probably of interest in making oxygen, but they do point out that the diamond electrode makes ozone pretty efficiently. And in that particular case, where you're generating ozone, you may be interested in, say, point source ozone generation or on-demand ozone generation, where you're generating ozone at the push of a button. In that case, you may have a large advantage over, say, a lead oxide electrode, which would have to be continuously kept from being corroded by some current. In this case, the diamond electrode would not have to do that. You just push the button and it would go. In the meantime, you could just leave it sit. So they're making that point. I don't know if I believe them or not, but I'm just saying that's what they're saying. So it's probably not a material that's going to be making large amounts of oxygen commercially. That's not how you make oxygen commercially anyway. You're not interested in producing oxygen by an electrolytic process. It's not you can get it for free, basically, from cryogenic processes. So they're more interested in ozone generation. But it does make hydrogen, not very efficiently, but it does make hydrogen also as well. I noticed there's a couple things that were of interest. One is that they said the Tafel slopes if you see on page 2359, it results in discussion of the second paragraph. The TAFL slopes range from 0.15 to 0.25 per decade. That's what that stands for. And so alpha A is equal to 0.25 for the anodic transfer coefficient. So for the oxidation of water to form oxygen, the alpha value is about 0.25. And A sub C is 0.3 for the cathodic transfer coefficient. And that A sub C is basically the hydrogen evolution reaction. So those both indicate that the reaction is, in at least the case for the hydrogen, you see that that's a reaction that indicates that the hydrogen is not being absorbed under the carbon or diamond surface. What's the ultimate lifetime limited to on this device, did they say?
800 hours. It depends on the doping though.
Yeah.
850.
Yeah. That's about 33, 34 days. Why did they say that the higher doping levels made the electrode last longer? How thick was this film?
5 micrometers.
Yeah. So it's a pretty thin film. When you think about it, it's doing its job for about 33 days under pretty rigorous conditions. But there is an ultimate limit. What do they say the limit? What's happening at the end? What's happening to cause it to fail?
We could grow a non-diamond layer at that level by increasing the concentration of the boron, which will...
Yeah, they said if you try to make the doping more than 5,000 ppm in order to extend the life or reduce the overvoltage, it doesn't work. So you don't get a diamond-like film anymore, right?
That would be mainly boron.
Well, yeah, it just doesn't make a diamond-like film. But that's not even at 5,000 parts per million, it ends. What's happening at the end? What's causing it to fail? Why does it fail?
Gasification of carbon
And what's that mean?
to CO2.
Right.
It's an oxidation reaction.
So in other words, you're basically oxidizing the carbon surface to carbon dioxide. And that's basically a parasitic reaction. You've got the main reaction that you're interested in, which is the oxidation of water, but at the same time you're causing a small amount of materials being oxidized to carbon dioxide. Now if you try to use a graphite electrode under the same conditions, that reaction would occur very rapidly. You'd form it very quickly. You would basically decompose a graphite electrode within probably a matter of hours of that thickness. So it's a very slow reaction. But it happens, they actually just try to have a description. Basically, what it's limited by is the amount of holes. The more holes in the material, the higher it's doped, the less likely it is that you're going to get formation of a carbon-oxygen bond.
Be very expensive to make since you're using chemical vapor deposition.
Well, it depends, I think, depends on the setup. You know, once you're set up to do it, it's not very expensive. The feed gas was ethanol and a little bit of boron, which is not very expensive relatively. So the setup is expensive. I mean, the instrument to do it is expensive, but I think once it's going, it's a very inexpensive way to do it. People are starting to do boron electrodes. You'll see that the people that they reference is a guy named G.M. Swain. If you look at the reference, he's reference number 8 and 4 and 5, and this guy Swain, Greg Swain is his name, has been using diamond electrodes for electroanalytical purposes, and so he's trying to convince everybody that they're good for that purpose, mainly because you don't have to worry about repolishing the electrodes, and they're very inert. They're kind of unusual. They don't act exactly the same as regular platinum or gold electrodes, but under certain conditions they act very nicely. They don't have to be resurfaced or polished or anything like that. Anyway, the other thing you see is that those electrodes are not smooth, and so sometimes describing the chemistry that's going on there in a mass transport way is very difficult to do, but it can be done. And that's a difference. You know, Swain would be working at current density levels that would be on the order of a few, maybe tenths or a thousandth current densities at the most, whereas these guys are working at the very high current densities. And so, whereas Swain sees that they act pretty well as electroanalytical electrodes, this guy was saying, well, really they're probably only good for ozone generation, a special application where the efficiency is relatively high. Everything else is not so great. Even though they're very wear resistant, they don't have good enough efficiency to be useful. Anyway, well, let's stop here, and you have the next paper. The next paper actually talks about a little bit about Marcus theory, and it's kind of an older one, but talks about some electron transfer rates.